We're going to get started in 1 more minute. I'm going to start now. We're going to get started now. Okay. Should I wait? Assalamu alaikum, everyone. So today's lecture is going to be the first main lecture of the course. It is linear regression. So before we get started with the main topic, I wanted to go over some of the topics we covered in lecture 1. So what is machine learning? Well, machine learning is using past data to make future decisions or future predictions. So we looked at 2 examples in the first lecture. The first example, we looked at 5 students, and we knew the hours that each student studied, and we know their exam score. And so what we did was we fit a line to these points. And so now, if we bring any new student and we want to know what is their exam score, all we need to do is plug in the hours that they studied into the equation of this line, and we will get their exam score. The second example, so this example is called regression, specifically linear regression. Now, this second example, we looked at heart disease classification. So we had about 100 patients, and for each patient, we know their age, their cholesterol level, and whether they have heart disease or they don't have heart disease. And then we have 2 new patients, and we only have their age and their cholesterol level, and we want to know if these patients have heart disease or they don't have heart disease. So what we did was very similar to the first example. We fit a line that separated the positive points, all the patients that have heart disease, from the negative points, all the patients that don't have heart disease. And so now, if any new patient comes, what we can do is we can plug in the age and the cholesterol level into the equation for this classifier, and we can mathematically figure out whether this patient has heart disease or doesn't have heart disease. So, what is common between these two examples? The common thing is, first, we looked at the past data. Second, we found patterns in the data. And third, using the patterns, we made a decision or we made a prediction on new data. So, what is the goal of machine learning? The goal of machine learning is to train a model to do a task well. What is a model? Well, we saw models on the previous slide. This line is a model, and this classifier is also a model. A model is like a math function that we want to find the best weights for. And so the weights is the slope and the y-intercept in the previous examples. Training is how we find the best weights for our model. And task is what exactly we want our model to do. So there are two things. The first is regression. If we want our model to predict a value, so some examples of that are 1, predicting exam scores, 2, predicting the steering angle of a car, how much the car should turn in order to drive on the road. And 3, if we want to predict what should the price of a house be, if we know how big is the house, where is the house located, how many bedrooms it has, how many bathrooms it has, and so on. The second type of task is classification. And classification is when we predict a specific class from multiple classes. So one class from, let's say, 10 classes. So we looked at predicting heart disease versus no heart disease. That is 2 classes. Then another example is if we want to predict what is the species of an animal. So we have a picture of an animal, and we want to know what type of animal is it. Is it a cat? Is it a dog? Is it an elephant? So we want to choose one class from 10 classes, for example. So how do we train a model? It is really important to give it a lot of data to learn from. So the data has 2 parts. The first part is called the input data, or the features. And this looks like images, video, text, or numbers. And labels is what we want to predict. So this could look like a real number, like regression, or a specific class or a category, like classification. And one assumption that we make about this data is that it is independent and identically distributed. What does this mean? Well, it means that one data point is independent or separate from another data point. The 2 data points, they don't depend on each other. So now I want to ask you all, from the first lecture, how many features did we have in the student exam score example? How many features? Let me go back to the first slide so you can see that No, 5 is how many data points. So we have 5 students, but how many features? Close. Well, it's actually 1 feature, because feature is in the student score example is how many hours the student studied. So we have one feature. And we have one label because we are predicting the exam score. Understood? Okay, so now how many features did the heart disease example have? Let me go back to that slide. How many features are here? Yes. And there is one label because we are predicting heart disease or no heart disease. So the two features are age and cholesterol level. Those are features. And number of students and the hours they spend. Now we are talking about that age and cholesterol level.
दो एग्जाम्पल्स है एक स्टूडेंट का एग्जाम्पल लिया है कि बच्चे कितने घंटे पढ़ते हैं कितने मार्क्स लाते हैं.
But in that second example, we are considering age as well as cholesterol level as features only. But in the first example, we are only talking about. Yes. So we can have one feature, two features, and features. We can have as many features. The more features we have, generally, the better data we have. It's good to have more features. But I gave a very simple example. So the first example, where we are predicting student exam scores, we have one feature. But in the second example, for the heart disease classification, we have two features. So now, how do we represent our data? So we can represent our data using matrices and vectors. So the data points we can represent with a matrix called X. So every row is a feature, and every column of this matrix is a data point. Let me give an example. So in our, so every column, for example, is a patient. For the heart disease example. So column 1 is patient 1. Column 2 is patient 2. Column 3 is patient 3. Or column 1 is student 1. Column 2 is student 2. And every row is a feature. So for example, column 1 is hours studied. Column 2 is student attendance. Or column 1 is age. Or column 2 is cholesterol level. And the labels for every data point, we store them in a vector or a list of numbers called Y. And so these two things together is called a training data set. Two things that I want to define is D. D is how many features we have, and N is how many data points do we have. So let's take an example from the student exam score prediction. So we saw that we had one feature. Now, let's make it more complicated and let's add two features. So, or let's add one more. So the feature that we are going to add is student attendance. So we have the percentage attendance for every student. So how do we calculate this? It's very simple. We take how many classes the student went to, how many sessions, and we divide it by the total number of classes in the course. And that's how we get these numbers. So now I want to ask you all, now what is the number of features and what is the number of data points?
Number of features number of data points.
Number of features is 2 and number of data points is. Yes. So how do we use a matrix and a vector to represent this data? This is how it would look like. So student one, this is the information for student one. So student one, Hassan, he studied for 1 hour and his attendance was 61%, and this was his exam score. This is student two, information, and student two exam score. Student three, information, student three exam score. This first row is all the just feature one, which is our study. The second row is feature two, student attendance. And then in here, we put all the exam scores for every student. So how do we represent a linear regression model? So as we saw in the first lecture, we can use the equation of a line. And the equation of a line is y equals mx plus b. But now we're going to use slightly different notation. So it is the same thing, but we are just using different variables. So for one feature, we have y equals theta 1 x1 plus theta naught. So theta 1 is m and theta naught is b. And this 6.80 is theta 1. And theta naught here is 41.1. So this is if we have one feature. But what if we have two features? So if we have two features, then it becomes y equals theta 1 x1 plus theta 2 x2 plus theta naught. So now I want to ask you all, what if we have d features? What is going to be the equation of our line? Maybe someone from the left side? It's quiet. You can take a guess. So
वन फीचर के लिए इक्वेशन लिखा है, टू फीचर्स के लिए इक्वेशन लिखा है. अगर n फीचर्स हो, b फीचर्स होंगे फॉर एग्जांपल, तो क्या इक्वेशन होगा आपको जस्ट गेस करना है. पैटर्न जो दिख रहा है उसी को फॉलो करिए.
Y is equal to theta 1 x1 plus theta n plus theta d.
थीटा 2 x2 थीटा 3 x3 up to थीटा d x
X
ऐसा नहीं बना.
So if we have d features, then we will have y equals theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus dot 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 plus theta d xd plus theta naught. Because we have d features, so we need d terms, and then the last term is the constant. So this is a nice summation, but what if we want something smaller, something more compact? So we can rewrite this long summation in terms of vectors. So now this long summation becomes y equals theta transpose x plus theta naught. And this looks very similar to y equals mx plus b. But now theta is not one number, but theta is a list of numbers or a vector of numbers. And so this is what theta looks like. And so you have theta 1, theta 2, theta 3, all the way to theta d. And theta naught is outside. And then we store the features for each data point also in a vector. So the first feature is x1, second feature, x2, third feature, x3, and we store all d features. So now, how do we know if one model is better than another model? So we talked about this a little bit in the first lecture. The way we know if one model is better than another model is by computing something that we call the loss. And the lower the loss, the better model we have. So now I want to ask you all, what do you think? Which model better represents this data? Is it the blue plot, the blue line, or is it the red line? How many people think it's blue? Raise your hand. How many people think it's red? So the answer is the blue line. And why? Because the line is closer to all of the points. You see right here that there's a lot of distance between the points and the line. So this right plot doesn't really represent the data as well as the blue one does. The blue one is better. So now that we have an intuitive understanding that the blue plot is better, how can we mathematically compute this? How can we have a number to say that this blue one is better than this red one? So we compute the loss, and one common loss function is called the mean squared error. And how do we compute this? So what we do is for each point that we have in our data set, we take the difference between the predicted value and the actual value, and then we square that number, and then we do the same for all of the other points, and then we add everything together. So for this example right here, we have 6 points in our data set. So what we will do is first we will do y1 predicted minus y1 actual, then square it, plus y2 predicted minus y2 actual, and square it, and then plus y3 predicted minus y3 actual, and then square it. Then we will do the same thing for all of the points. And this is called the mean squared error. So now let's take an actual example with numbers. So we have the line that we found in the first lecture, y equals 5.5x plus 45.5. And we want to compute the loss for this line. So this is the math. So first, we do the predicted value for Hassan. So he studied for 1 hour, so we want to know what is his exam score. So F1 minus 48 squared plus, this is the second data point, F2 minus 56.5 is the actual score squared, plus F3 minus 59 squared, plus F4 minus 67.5 squared, plus F5 minus 76.5 squared. And then we do the math, and we get that the loss is 6.05. Does this make sense? Do you guys understand? I can explain it one more time if it does not make sense. If you understood, use a thumbs up. If you did not understand, use a thumbs down. Which part? The last line? Oh, so something I forgot to mention is once we calculate the sum of all the differences, we want to take the average. So that is why there is mean squared error, because we take the average. So then we divide by how many data points we have, and we have 5 data points. So then we divide by 5. Was that what you were confused about? Or you were confused about something else? Any other questions? It's okay if you did not understand, because I'm not going to move forward until everyone understands this. Okay. If no questions, I'm going to move forward. So how do we find this? We know how to tell if one model is better than another model, but how do we actually find the model with the minimum loss? So we have this loss function, and this loss function is a function of theta, which is the weights of our model. So in math class, usually we have function of x, but now we don't have a function of x because we already have x. X is all of our data points. We have a function of theta. We want to find the weights. So how do we find the minimum of a function? How do we find the critical points? So to find the minimum of a function, we just take the derivative of the loss with respect to theta, and then we set it equal to 0, and then we solve for theta. This is just like calculus class, where you have a quadratic function and you want to find the minimum. So now I want to ask you all, just to make sure we understand, what is theta in this example? you can talk with your peer, someone next to you. And then I will give 1 minute for everyone to discuss. So please talk with your neighbor. If you aren't sitting with someone, please sit next to someone. Does anyone have an answer? Take a guess. It's okay if you're wrong. Okay, so theta in this case is 6.80 and 41.1. It's our slope and our y-intercept. So I showed you magically in the first class, we came up with this line, but I didn't show you how we actually find this line. So what we are trying to find is we are trying to find M and B, and we don't know what M and B are. So I was trying to see if you guys understood that we are trying to find these two numbers, 6.80 and 41.1. So now that we know that we have to find the minimum loss, let's actually solve for this theta that gives us that minimum loss with differentiation. So there are 5 steps. So the first step is we have to rewrite our equation for the line, y equals theta transpose x plus theta naught as y equals theta transpose x. This makes it very easy to do our calculations. The second step is we need to rewrite our loss function, the mean squared error, from summation form into matrices and vector form. And this also makes it very easy for calculation. Finally, we take what is called the gradient of this loss with respect to theta. And if you don't understand what is gradient yet, that is okay. Think of it right now as a derivative. And then once we find this gradient, we set it equal to 0. And then we find the theta that minimizes this loss. So what is J? J is called our objective function that we want to minimize. So in this example, J is actually just L. But in future examples, it'll look a little different. So just think of J as L. They're the same thing. So first, we want to rewrite this y equals theta transpose x plus theta naught as y equals theta transpose x. So how do we do that? Well, it's very simple. We just add one more element to our vector of thetas. So at the end, we have a theta naught, and then we add another feature to our data set, and that feature is just 1. So if you were there yesterday, in yesterday's lecture, Rose went over how do we multiply these two vectors. So what we do is we take the first element and we multiply it with the second element. And then plus the second element in this one multiplied by the second element, plus theta 3 x3, all the way down to the end. So if we multiply these two vectors, we actually get back the same equation that we started with from the beginning. But this just shows that we did not change the equation. It's still the same. We just rearranged the formula. So the second step is to rewrite this loss function as 1 over n x tilde theta minus y transpose x tilde theta minus y. So the first thing we do is we substitute our predicted y value, theta transpose xi, into our formula for the loss. And so then we get the loss as 1 over n sigma I equals 1 to n theta transpose xi minus yi squared. So this is in summation form. But now we're going to rewrite this with matrices and vectors. So the first step we do is, if you remember our training data set, we had a matrix called X, and we had a vector called Y. And the matrix X stored our data points. So in that matrix, you saw that each column is one data point, and each row is a feature. So what we do is we just take the transpose, and what that means is we just flip the rows and the columns. Think of it as if you have this matrix on a piece of paper, you just flip the paper sideways. And we do the same thing with the labels Y. And so now we get this new matrix and this new vector, x tilde and y tilde. So that's step 1. Then I just want to show you how does this part equal this part right here. So if you remember, for matrix multiplication, we multiply this row times this column. So the first row times this column, and we get the first element. So let's confirm that this works. So x1, theta 1, x plus x2, theta 2, plus x3, theta 3, plus dot 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 xd, theta d, plus 1 times theta naught equals y1. So, or minus y1. So this is exactly the equation that we saw before, but it is just the y, we're just subtracting the labels y. So this shows that this form right here is the exact same thing as this form. But the difference is that we're doing it for all of the points at once instead of doing it for every point one by one. And this makes it very efficient. So now you might be wondering, where did this square go? Why isn't this square in this part right here? Well, when you have two vectors, y1, y, let's say we have y transpose y. So then if we multiply these two vectors together, we will get y1 squared plus y2 squared plus y3 squared plus y4 squared, and so on. And that is the same thing as y transpose y. So you can see this summation looks just like this summation. And then this transpose looks just like this. So this is justification for how we can get from this equation to this equation. It's the same thing. So before we take the gradient, I want to just review what is a partial derivative. So in math class, you looked at f of x. So that function is just a function with respect to one variable. F of x equals x squared plus 2x plus 4, or f of x equals 5x plus 7. It's just one variable. But what if you have a function with two or more variables? So like this example, f of x, y equals x squared y plus y cubed. So how do you compute the derivative for this function? To do that, we first compute one derivative at a time. So we compute the partial derivative of the function with respect to x, and then we compute the partial derivative with respect to y. And then we store it in a vector or a list, these two derivatives. So we see this example. First, we compute the partial derivative with respect to x of this function. So we treat y just like a constant. So the derivative of this is going to be 2xy. And then we compute the partial derivative with respect to y. And we treat x as a constant. So then we get x squared plus 3y squared. And so these are our two partial derivatives. So then what is a gradient? Well, a gradient is just a vector that points in the direction of the greatest increase of the function. And the gradient is just all the partial derivatives, but in one list together. So if you have three variables, x, y, and z, then the gradient is going to be a list of the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. And if we have two variables, then we just have two partial derivatives in our gradient. And for a gradient, we use this symbol, which looks like an upside down triangle. So now let's compute the gradient. This is very similar to what we have done in math class. So we just take the gradient with respect to theta. And so this first, we take the gradient of this function. And so we get X transpose. And then because of the chain rule, we still have this X theta minus Y. And because we said that this function is just like a squared function, there is a 2 that comes down. Just like when you take the derivative of x squared and you get 2x, it's the same thing. So then we have computed the gradient and we set it equal to 0. And then we just do some algebra to find this theta. So first we do some distribution. So it becomes x transpose x theta minus x transpose y equals 0. And because we have 0 on the other side, if we just divide both sides by 2 over n, this goes away. So we don't have this anymore. So then we move this term to the other side of the equation, and we get x transpose x theta equals x transpose y. And then, just like in regular algebra, we need to separate theta. We need to solve for theta. So just like how we divide both sides by x transpose x in regular algebra, in linear algebra, that is called taking the inverse. So we take the inverse on both sides, and this is our theta. Theta equals x transpose x inverse x transpose y. Is that clear? So now we are going to look at other loss functions. So you may be wondering, why did we take the squared differences, the sum of the squared differences? Why did we not just take the sum of the differences? So we're going to try that in this example. So let's have a data set with just these 2 points, this point and this point. So now I want to ask you all, what is the best line that fits this data set? What is the equation? Or what is the slope? We have 2 points. What is the slope if we connect the 2 lines, the 2 points? Sorry?
इन दोनों पॉइंट्स को अगर आप कनेक्ट करोगे तो x एक्सिस से उसका एंगल कितना बनेगा 180 बनेगा।
Yes. So the line is just y equals x. And it may be hard to see from the back, but this is a 0. So the y-intercept is also 0. So the line is just, sorry, y equals 0. Yeah, that is the line. Y equals 0x, but it is just y equals 0. So Yes, the line that best fits this data set is y equals 0, and the line has a slope of 0. So now I want to ask you all, what is the loss of this model if we take the sum of all of the errors of all the points, the sum of the differences? Yes, the loss is 0. But what is the loss for the slanted line?
जितना वहाँ पॉजिटिव है डिफरेंस उतना है उसका नेगेटिव डिफरेंस
Sorry, louder? Yes, the loss is 0. For those of you who might be a little confused, the reason why it is 0 is because we take the difference between the predicted value and the actual value. So we take the predicted value, this is maybe 0.35, minus 0, which is 0.35, plus negative minus 0.35, minus 0. So then we have minus 0.35 and plus 0.35. We add them together, we get 0. So that was just showing that. So when we add these two differences, we get 0. So how can these two lines have the same loss, but they're different models? So any line that passes through the midpoint of these 2 points will also have a loss of 0. But we know that for a fact, these lines don't represent the data because there is only one line that represents the data. And the line that represents the data passes through these 2 points. So that means that if we use the sum of the differences, that is a bad loss function because we're going to get the wrong model, or there is a possibility that we can get the wrong model. You may be wondering, why don't we just take the absolute value of the sum of each difference and then sum them together? But we have another problem, which is the absolute value function is not differentiable at x equals 0. So it's not a good function, not very convenient to use. But if we square the differences, then we can still sum all of the errors together without the positives and negatives canceling each other. And another benefit is that this squared sum is also differentiable everywhere. So now I'm going to go on to another topic, which is called regularization. So let's look back at the solution that we found using linear regression. This is called the full matrix solution. It's called a complete solution. So I want to ask you all, what could go wrong with this solution? What can happen that makes this theta impossible to compute? which, yes. So if this inverse does not exist, then we can't compute this. So yes, that is correct. So sometimes X transpose X may not have an inverse. So we run into a problem here. So now let's look at the reasons why can this happen. So when the features are highly correlated with each other, so they're related to each other, then X transpose X has a lot of zeros. And that leads to the inverse being undefined or having really big values. So let me give you an example. So for the student exam score prediction, we added another feature called student attendance. And so we can see that both of these increase as the exam score increases. So there is also a correlation or a relationship between the hours studied and the attendance. If a student comes to class more, they might study for more hours. That is not always true, but in this data set, that is true. So exam score can depend on the hours studied and the attendance in the same way. So this is a visual example. So we have two features, x1 and x2. And if we plot them, we get a straight line. So this is showing us that x1 and x2 are also highly correlated with each other. And if these features are highly correlated, then we have an unstable model. So this is an example where we have an unstable model, and you can see these two numbers, negative 5 times 10 to the power 15 and 5 times 10 to the power 15. This shows that our line has a very, very high slope, which is very unstable. But if we apply something that I will discuss in the next slide called regularization, then we can have a stable model that has a small slope. So how do we do this? So to do this, we are going to add a regularization term to our objective function, and that is going to make our model stable. So sometimes, if we know what we want to regularize towards, this is called a prior. So if we want to regularize towards a prior, we'll do theta minus theta prior squared, norm squared. And so when we put this in our loss function or our minimizate, we're trying to minimize this function. We're going to try to minimize this difference as much as possible because we want this to be close to 0 as much as possible. The other case is if we don't know what we want to regularize towards, then we just do R equals norm theta squared. And this is most of the time. And another reason why we use regularization is because it also helps with something called overfitting. And what is overfitting? Overfitting helps our model from being too attached to our data. So we do want our model to fit our data, but we don't want it to fit our data too much that it's not going to generalize to new unseen data. So if it fits the model, if the model fits the data, too well, then when we have a new data that comes in and we want to predict that new data, then we're going to have a very poor prediction. So regularization balances memorization of the data with generalization. So now our objective function J becomes the sum of the loss and also the regularization term. So this is our objective function J. This is our loss. This is just the mean squared error that we saw before, so it's nothing new. And then we have a new term called the regularizer term. And this is lambda norm theta squared. What is this lambda, you might ask? So if lambda is 0, then we have the same loss function that we had before. But if we have a non-zero value of lambda, like 0.5, 0.7, or 1, then we have this regularization term. So we set this value of theta by ourselves to decide how much regularization we want. So now let's derive the new solution for theta that minimizes our objective function. So we do the same thing. We take the gradient with respect to theta of this objective function J. So if we have two functions, then the gradient is just going to be the sum of the gradient of those two functions. So we took the gradient of this function and we get this term. And then we take the gradient of this function and we get this term. And then it's just math. And I think you all can follow this. We just do distribution here. And then we divide the whole equation by 2. And then we move this term to the other side of the equation here. And then we multiply both sides by n. And then we take theta common from these two terms. And so because n theta is just a constant, when you take theta common, you need the identity matrix. And then we take the inverse on both sides, very similar to dividing both sides by this term. And then this is our new theta. So the difference between this one and the previous solution is we have this additional term called n lambda I. And this helps this whole term become invertible. So now we can compute theta. So now we have concluded the lecture for linear regression. And if you have any questions, you can come up now, and we will have lab starting at 11:30. Rose? 11:30. So our lab starts at 11:30.